All right, so in order to really start to think about what the probability is for having a certain trait based on genotypes, we need to start thinking a little bit about probabilities and statistics. So we're going to use probabilities to determine the likelihood of getting a specific genotype or phenotype if we know what the parent's genotype or phenotype might be. So in order to do this, we need to think about the multiplication rule. So if the events A and B are independent, the probability that they occur together is the probability of A times the probability of B. So in other words, if we need A and B at the same time, or we want these two traits at the same time, or whatever it might be, then we look at the probability of each by itself, the probability of A and the probability of B, and we multiply that together, and that would be the probability of AB, or A and B. All right, so let's think about this a little bit further together. So, but first a reminder, we're talking about if events A and B are independent, right? So that means that the events happening in B are not dependent on what happens in A. These are two independent things. So let's think about this with regards to dice, right? So when rolling a dice, what is the probability that you will roll double fours? So you're rolling two dice. What's the probability of rolling double fours? Well, let's think about this together a little bit. Let's first think about what's the probability of rolling 1 4. So you have one dice now. What's the probability of rolling a 4? Well, the probability of rolling a 4 is 1 out of 6, right? So it's the events that you're looking for divided by the possible events. So to roll a 4, you can get a 4, and that's 1 out of 6 options in that dice. And so this would be what we're considering as event A. So the rolling a 4 here, event A. And then rolling a 4 here would be event B. And so the probability of rolling a 4 with event B is also 1/6. And so the probability of A and B, when you hear the word and, the probability of A and B is 1/6 times 1/6, so the probability would be 1 out of 36 for rolling double fours. Right? Probability of A, probability of a 4 on this dice was a 1/6. Probability of B, probability of a 4 on this dice was a 1/6. So probability of double fours is a 1/6 times a 6. 1 out of 6 times 1 out of 6 equals 1 out of 36. Right? So that's the multiplication rule. And the hint for multiplication rule is when you hear the word and. What's the probability of this and this occurring? Then usually, almost always, you're going to multiply. But now we have the additional rule. This is the probability of the realization of one or more mutually exclusive events. So it's A or B, right? Not A and B, that was multiplication. Now it's A or B. So when you have that probability of A or B, then that's the sum, adding rather than multiplying. And so mutually exclusive means if you have one, you can't have the other. So let's think about this for a second. What's the probability of rolling either a 3 or a 4 with the dice? Well, again, we can think about this separately. We have the probability of rolling a 3 is 1 out of 6. The probability of rolling a 4 is 1 out of 6. You can only roll either a 3 or a 4. You can't roll both because it's one dice, so therefore they're mutually exclusive. If you roll a 3, you didn't roll a 4, and vice versa. So what's the probability of rolling a 3 or a 4? Well, it's 1 out of 6 plus 1 out of 6 plus 1 out of 6, or 2 out of 6, or 1/3. Because now you have two options out of 6, basically. So the probability of rolling either a 3 or a 4 is the sum of each individual probability. 1/6 plus 1/6 give us that third. So the hint here is look for the key indicators, and or. And so probabilities that use the multiplication rule are going to say and. What's the probability of this and this, right? Either explicitly stated or implied. Probabilities that use the addition rule have or. So what's the probability of this or this? And again, explicitly stated or implied. So let's put those together. So when we know those two rules, we can start to really think about most probabilities. So what's the probability that you will roll doubles, any double? All right, let's think this through again. So if I'm rolling any double, it means I have to roll a 1 and a 1, right? So a double, the probability of rolling a double 1 is 1/36, right? We did this already with the 4s. 1 out of 6 times 1 out of 6, because I have to roll a 4 and a 4, or a 1 and a 1. So my probability of double 1s is 1 out of 36, but my probability of double 2s is 1 out of 36. Double 3s, 1 out of 36, double 4s, each double is 1 out of 36 probability. But if all I'm trying to do is roll doubles, I could roll double 1s, or double 2s, or double 3s, or double 4s, or double 5s, or double 6s. So that means basically we have 1 out of 36 plus 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 1 out of 36. Again, ORs, we're adding them up. So that's 6 out of 36, so the probability is back to 1 out of 6. Because I have to calculate the probability of double 1s, 1 out of 36, and then double 2s. Each of those is 1 out of 36, but it can be 1s or 2s or 3s or 4s or 5s or 6. So 6 out of 36 total. Okay, so let's put this a little bit more simply, maybe. So what's the probability that with 2 coins you will flip 2 tails or 2 heads? All right, so we've got 2 tails or 2 heads. All right, so let's think about this for a second. What's the probability of 2 tails? Well, first we need to know the probability of a tail. So if you flip a coin, the probability of getting a tail is 1 out of 2. Right? So this probability here would be 1 out of 2. And if we're rolling double tails, it has to be a tail and a tail. So a half times a half. I would have a 1 out of 4 chance of flipping double tails. A half times a half, because I have to flip a tail and a tail. What about 2 heads? Well, a half and another half. For each head, it's a half probability. And if I'm doing 2 heads, I need a head and a head. So a half times a half is a quarter. So I have a quarter over here for my double tails. I have a quarter over here for my double heads. And it's double tails or double heads. So do my quarter plus a quarter. Right? And so basically that means that overall it ends up being a half, because the probability of double tails was 1 out of 4, probability of double heads was 1 out of 4, double tails or double heads, you hear the word or, and you add quarter plus a quarter is a half. So basically a coin can be thought of in terms of a heterozygous parent with 2 different alleles, right? So if you're a heterozygous parent and you have a tail allele and a head allele, then we can basically just put together a Punnett square, right? So if we put together that Punnett square, we have a head and a tail on one side. So I tried to save you the pain of watching me try and draw with my cursor here, but we basically, in a way, have a Punnett square. So this coin could give me a head or a tail. That's like a parent being heterozygous. I could have a capital A or a little a or whatever it might be. But this coin has 2 options. This coin has 2 options. And so put them together, I have a 1 in 4 chance of getting double heads. I have a 2 in 4 chance of getting a head and a tail. And I have a 1 in 4 chance of getting a tail, or double tails. So if I'm looking at double tails, the probability of double tails, so again, now you are watching me try to draw this, but the probability of double tails is 1/4. Right? The probability of double heads is also 1/4. And we can see that in our Punnett square. You can probably see that when you think about probabilities. So the probability of double tails or double heads, what do you do when you hear that term or? Well, when you hear the term or, you add. So that's a quarter plus a quarter. So the probability of double tails or double heads would be a half, or 2/4, if you will. Right? And so basically we're putting together our ideas of the multiplication and addition rule. Multiplication and addition or. And that's kind of what happened here. This heads, this double heads was a quarter because I had to get a head from this parent and a head from this parent. The probability of getting a head from this parent, right, or from this coin, flipping a head, was 1 out of 2. And the probability from this coin was 1 out of 2. So to get double heads, I needed a head here and a head here and a head. So 2 heads. head and a head. When you hear and, you multiply. So a half times a half, that ends up being 1/4 possibility there. All right, so if we take a look about here now, what's the probability with 2 coins? You will flip 2 tails or 2 heads. That's kind of back to where we were before. All right, we've got 2 heads. What about 1 head, 1 tail? Well, same idea. Now it's a half times a half because I needed a tail from here and a head from this coin. Half times a half. There was a quarter, but I could have it the other way. So a quarter plus a quarter, back to a half. And if we go back to our Punnett square, which unfortunately got erased here, then that would show you again you have a half. All right, so let's put this together. If 2 parents are heterozygous for albinism, right? So albinism just basically means lack of pigment. So a big A, we'll define our allele sealer. A big A is normal pigmentation. A little a is the allele for albino. And so if you're heterozygous, then you would be big A, little a, right? That's heterozygous. And so if that's the case, then from this parent, I could get a big A or a little a. From this parent, I could get a big A or a little a. So that's setting up my Punnett square. And so when you fill out that Punnett square, these are the possibilities there. But basically, we know now that you have a 1 in 4 chance of being big A, or a 1 in 4 chance of being little a, and a half chance, 1 out of 2, of being heterozygous. Right? But we can also kind of put that together. What's the probability of big A, big A? Well, it was a half, right? 1 out of 2 from this parent, and I had to get a big A from this parent and a big A from this parent. So there's multiplication, a half times a half. That's kind of how I get my quarter there. Right? So for heterozygous, I could be big A, little a, meaning I needed a big A from this parent and a little a from this parent. Right? That was half times a half, quarter, but it could be the other way around as well. The little a came from this parent instead, big A from the other parent. Again, half for this A, half for this A, there's a quarter. And the probability of little a is also same idea, there's a quarter. But now we can start to put together the OR, right? So what's the probability of being heterozygous? Well, I could have this genotype or this genotype. So a quarter plus a quarter, I know I have a 1 out of 2 or half a chance of being heterozygous. Well, and what if albinism is recessive, right? We know the only way to be an albino is to get this genotype from both parents, and that was a 1 in 4 chance of getting that genotype from both parents if both parents were heterozygous, right? And we did that with the Punnett square. And we also knew that you had a 3 out of 4 chance of not being albino. Well, why is that? Because if I'm looking at phenotype, this person has normal pigmentation, this person normal pigmentation, this person normal pigmentation, this person was albino. So what's the probability of having normal pigmentation or of not being an albino? You could be this genotype or this genotype or this genotype. So a quarter plus a quarter plus a quarter, that's 3/4. Well, we were doing that automatically because we knew that we could be in this group, all 3 of these basically were not albino. And that's how we got our 3/4. So you automatically have been using the multiplication and addition rules already when you've been doing Punnett squares. So why have we been going through this so much? Well, because this is how you can really start to work out multiple traits at a time, right? The fact that we know that we have these multiplication rules, these addition rules based on and for multiplication or for addition, we can now look at any number of traits. We can look at 20 traits at a time, right, and think about them all together. But the way you would do that is you would look at each of those traits individually using individual Punnett squares and then using our multiplication and addition rules, right? So let's think about this. Now we're talking about dihybrid crosses. A dihybrid cross is a cross between parental strains that differ between 2 characteristics, right? So in this case, we've got violet or white flowers, right? So one is violet or white, and violet is big V, white is little v because violet's dominant over white. And then we also have the flower location. So axial just means the flowers along the side of the stem. Terminal means the flowers at the end of the stem. So axial, big A, and the terminal, little a. So axial is big, is dominant over terminal. Now, if we're looking at these 2 traits, well, the 2 traits are each have their own gene sets. So this flower could be big V, and big A, right? These are the two genes we're looking at, and we're diploid for each of these genes, right? You have 2 alleles for violet, or 2 alleles for white, and 2 alleles for axial, and 2 alleles for terminal. And so when the gametes are made, each of these sets of 2 gets turned into 1, right? That's meiosis. Every gene gets separated out from diploid to haploid, so we're not going to have 2 V's anymore, we're going to have 1 V now. We're not going to have 2 A's anymore, we're going to have 1 A. Same over here. And that way, when you get put together, you have 2 V's again, all right? The next generation's back to diploid because haploid plus haploid in the gametes makes diploid. And so in this case, now this plant would be heterozygous for the violet flowers and heterozygous for the axial. Now, this seems to start to get a little bit difficult here, but we know that these traits are independent because of the independent assortment. So as long as these traits are on different chromosomes, or at least far enough apart on the same chromosome so that crossing over has had a chance to occur, then what that means is just because a big C lined up over here doesn't mean the big A has to. It's possible, but all your chromosomes could line up this way, in which case one gamete got all the big C, A, B's, one got the little ones, and so forth. Or they could have lined up this way, and so now you have a different combination, or this way. But the point of it is, the allele you get for gene A has no bearing on the allele you get for gene C or gene B because they can all line up independently and separately. So now we can start to put those addition and multiplication rules together because of the principle of an independent assortment, because the allele you get from one gene has no bearing on which allele you'll get for another one. So if we start to cross this generation here, if one allele got the big V, it doesn't mean it has to get the big A. It could get a big V. So we have multiple options for these alleles, right? We could get our allele options are I could get a big V and a big A. Remember, the gametes after meiosis, they're only going to have one of each. Or I could have a big V, and it could be with a little a, right? One of each. Or I can have a little v with a big A, or a little v with a little a. Either way, these are my gametes because what was diploid end up being haploid. And so, but I could get a big V or a little v, 50-50. But whether I got a big V has no bearing on if I get a big A or a little a. I can also get a big A or a little a. That's 50-50 as well. And so I end up with these 4 equal options in the combinations. But we can start to think about this a little bit further. And we can start to see what possibilities we would have. And this is the great thing. Because we know of those multiplication and addition rules, we don't have to worry about these multiple traits together. We take each of these traits individually, and then we can start to use our addition multiplication rules there. All right, so let's take a look here, and let's look at each of these things individually. All right. So if I'm doing this, then I'm looking at the V's by itself. So if this big V little v is crossed with this big V little v, then I have the possibility of getting a big V or a little v from one parent and a big V or a little v from another parent. And when I start to put those through, this is the standard Punnett square, big V, little v, and again, I can't draw on a computer, but you guys can do your Punnett square with me. But this is basically what we would get, right? And so we do that for the V's, and then I need to think about the A's, so we do that for the A's. And both parents are heterozygous, so again, I can get a big A or a little a big A or a little a from this parent, right? Each parent's heterozygous. And when I run my Punnett squares through in the way that you guys know how to do this by now, and you should be doing it with me, you can figure out what the genotype possibilities and the phenotype possibilities are. Wow, this is getting pretty ugly, but that's all right. You guys got the idea. All right, so you guys know how to do a Punnett square. We now have two traits, but we don't really care. We're doing them individually one at a time. So now I can look at this. What's the probability of getting a flower with the genotype VVAA? Well, I need VVAA. So what I'm looking for is what's the probability of big V, and what's the probability of big V? Well, I look over here, and the probability of big V was 1/4, and I can see that from my Punnett square for the big V, or for the traits with the V's, right? Now, what's the probability for big A, little a? Well, I look at this Punnett square over here. All right, so at this point, I know that my probability of a big V is 1 out of 4. Right, there's my Punnett squares right there. I know the probability of a big A, little a. Right, I know the probability of big A, little a. Sorry, real quick. There we go, laser point. Probability of a big A, little a is a half, right? And so if I need to be big V, and big A, little a, I just multiply. So I have a quarter for the probability of big V. I have a half for the probability of big A, little a. So a quarter times a half basically means 1/8. I have the probability, I have a 1 in 8 probability of getting a flower with this genotype. Right? Probability of VV and AA. What about the probability of getting a violet flower with terminal flowers? Remember, violet was dominant and terminal is recessive. So the probability of getting a violet flower was 3 out of 4. All three of these are violet, but only this is terminal. So 3 out of 4 times 1 out of 4, because I need to be violet and terminal. 3 out of 4 times 1 out of 4 is 3 out of 16. So the probability of getting a violet flower with terminal flowers would be 3 out of 16. And we know that because we just figure out the probability of each part alone. Violet was 3 out of 4. Terminal was 1 out of 4. And multiply. 3 out of 16 is the total. Right? So what I want you to do is figure out the F2 probability based on what we were just doing. So based on this cross here where we have heterozygous for both traits crossed together, what's the probability for a plant making violet and axial flowers? What's the probability for a plant making violet and terminal flowers? And white and axial, white and terminal. So what are the probabilities of all of these different things? This is our F1 generation mated together, right? The parental generation was the homozygous ones. The F1 generation is this heterozygous, and the F2 generation would be the result of that. So what are the answers to that? Give you pause the video for a couple minutes and practice that and see if you can get that. All right, excuse my crazy writing here again, but we know that the probability of a violet flower is 3 out of 4. We know the probability of a white flower is 1 out of 4. And we can see that, again, back here with our Punnett squares. Probability of violet flower was 3 out of 4. White flower, only 1 out of 4. Using the same thing, we know that the probability of the axial flowers, which was dominant, is 3 out of 4. Terminal is 1 out of 4. And so if I need to know the probability of a violet and axial, well, now we multiply. 3 out of 4 times 3/4 is 9/16. Right? For this one, violet and terminal, 3/4 times 1/4, 3/16. White, 1/4, and axial, 3/4. 1/4 times 3/4, again, 3/16. A white and terminal, both of those are recessive, so 1/4 times 1/4 gives us the 1/16. And the great thing about this is you can look at any cross with any number of traits, and we now know how to do this, because all you're going to do is look at each trait individually. Set up a separate Punnett square for the A's, a separate Punnett square for gene B, for gene C, separate one for D, and separate one for E, and so forth. And then you can figure out the probability of this genotype, because it's the probability of this from your Punnett square for A's times the probability of this times this times this, and so forth. Right? So you look at each probability individually, and if you need to, feel free to do a Punnett square. But this is the genotype I'm looking for, little a, so I need to know what that probability is. Big B, little b, big C, big D, and little e, right? And so if you look at the probabilities individually for each of these traits, right, and do the Punnett squares if you need to, but what's the probability of little a? Well, if we look at all these probabilities, we get this. Hopefully you got that from your Punnett squares. And since I need this and this and this and this and this, I just do those probabilities together, and that would be my answer. So on a celebration of learning, I could give you any number of traits, all right, as long as I give you the genotype of the parents and the phenotype or the genotype we're looking for in the children, then you know how to do it because you just do each one individually. And then we use our adding and multiplication probabilities together, right? Figure it out. And you could do this for phenotypes too, as long as you knew what the phenotype we were looking for was and what's dominant, what's recessive or incomplete dominant or whatever it might be. Again, you just look at that probability individually, and then you usually multiply them together, because if I want a child or a offspring that this genotype, what's the probability? Well, it's this and this and this and this and this.